In the lithography lecture series, we are going to look at electron beam lithography in this particular lecture. First of all, let's look at why we need electron beam. So far, all our discussion was around optical lithography, where we use light as the illuminating source for transferring pattern. But here we are going to use electron beam, right? So it's not going to be photons, but electrons for pattern transfer, right? In particular, we are going to do writing, right? And let's look at the idea behind electron beam lithography. But first of all, let's look at the rationale behind going to electrons as opposed to photons. So the whole idea of moving towards electron beam lithography, or looking at alternate form of patterning than light, is resolution, right? So here in the table and also in the picture, you can see there is wavelength and then there is associated energy. So the wavelength strongly depends on energy of the fundamental particle we are trying to use. So far we used light, and this is what the wavelength was, and then the energy was about phi eV. But your wavelength is the one that is restricting. If you remember, our resolution depends on the lambda over Na times k, right? So your lambda was one of the restricting factor here. So how to reduce this lambda was one of the resolution enhancement technique, right? So you can use X-rays as well, right, to improve the resolution. But then we will see later in alternate lithography that these X-rays, how difficult these X-rays are to handle and so on. But if you look at the particles, right, so electrons and ions, there the energies are very high, right? So 20 keV and 100 keV energy. So that brings down the wavelength. So that means your waves are very small, right? And with those you should be able to define very finer features, right? So this is the left side image captures how small you can define the pattern. So you can see here electrons and ions, you can finely define or make a very pencil beam, right, as opposed to photons that we use by focusing and so on. So X-rays are a different class, so we will discuss that later in alternate lithography techniques, but for now, as we discussed, the particles with very high energy can be used for high resolution patterning. So this is a comparison between electron beam system and the projection system. On the left side, we have seen this multiple times, where you have the source, you have illuminating optics, you have the mask, and then you have the projection optics and the wafer here. But if you look at on the right side, the electron beam system, it's much more complicated, right? But the elements remains the same, right? So there is electron gun, that is the source, and then this is the condenser optics or illuminating optics, right? And then you have the aperture and the lens optics, more or less acting as projection. But since there is no mask involved, right, in electron beam lithography we don't use mask, right? So there is no mask, and that's the reason why we call it as mask less process, right, maskless litho. So you don't need any mask, right? So how do we pattern it then, or structures then? So the way we do that is by using this pattern generator and controlling the electron beam, right? Unlike optical litho where we do printing, here we do writing, okay? So the right word to say is e-beam writing, right? So you use a pencil of beam here to write the patterns, right? So we will look at this configuration little bit detail later in this lecture, but let's look at first element in the whole system. So that is the electron source itself, right? So where do we generate these electrons from, right? In optical sources, we use lasers, right? Excimer laser or even lamps, mercury vapor lamps were used. But let's see what are all the sources that we can have here. There are predominantly two type of source. One is the thermionic source and the other one is field emission. The whole idea here is how to give enough energy to the electron sitting inside the material to take it out, right? That means how do you take it over the work function and take it out of that material, right? So one way of doing that is by heating the material. So when you heat it enough, then you can overcome the work function barrier and then you can take the electron out. The other way to do that is by applying enough electric field. When you apply very large electric field and the electrons tunnel through this barrier, and then you should be able to get the electron out, right. So you can also do combination of these two, so the thermal and field emission together. So that is what predominantly done, where you use tungsten as the source. When it is heated, it will emit ions, electrons, and then that tungsten is covered by zirconium oxide, right, which helps you in reducing the work function. So the work function can be reduced somewhere between 4.5 eV to about 2.5 by this coating. So the lower the barrier, you need less energy to extract the electrons out, right. So that's not only the reason why we like this. The spot size, there are various factors, right. So the brightness is nothing but how much power you get out, right, and the size, right, how small is your source size, and then the energy dispersion, right. Energy dispersion is again a very important parameter of your optical source, electron source. The reason for that is we saw this partial coherence, right. So when you take a light source, if this is lambda, so you will have a certain width, right. You will not have a single line, right, laser line. You will have some delta lambda, right. Similarly, in electron beam, ideally you want energy to be just E, right, but light sources are not really ideal, so you will have some delta E. So this is what energy dispersion is all about, right. So what is the dispersion that we have, and then the brightness is how much electrons you can extract out, and the size is also important, right. The finer your beam, your finer your structures are going to be, right, and based on the type of sources, this size could vary, right. And the other important thing is the vacuum required, right. So you cannot, unlike optical lithography, you cannot use electron beam in atmospheric pressure. So you need to go to low pressure. So that is again a constraint, right. So if you look at other sources, though you have so if you look at lanthanum bromide, you have 10 micron as your source, which is pretty good, right. You have a very sharp focus, but then the vacuum level needed here is very aggressive, right. So you need to spend a lot of energy in getting the vacuum here. However, if you look at tungsten thermionic type emitters, 25 micron, a reasonable feature size, but 10 to the power of -6 torr is the required vacuum level, which is typically used in lot of vacuum processes. So it's not just about source size, it's also about the vacuum level one can reach and then the energy you want to spend on those as well. So on the bottom right, you have a typical configuration of an electron source. So where you have the tungsten crystal that is sitting there and which is emitting your electrons, and this emission is mediated through the extractor and then the suppressor. This is just to focus the beam, and then you have the whole circuitry here, right. So you have the filament current, right, which we have to give, and then this is the the emission current, right? This is the accelerator, that is the potential difference between this plate and then your source is going to give you how much extraction current you can get, and then you will have acceleration, right? So once you get it out, then you accelerate the beam, and the accelerated beam can be achieved by varying the voltage difference between the extractor here and your accelerating voltage. So this is how we do the electron emission source configuration. And next comes the vacuum tube itself, or the column itself. So there are three fundamental elements here. One is the electron source, which we just saw, and then there is objective lens, and then the beam deflection unit, right? In addition to that, you have lot of apertures and so on, but let's look at what are all the things that we have in this column, right? Primarily the whole idea of this electron beam column is to control the electron beam, right? So the what we had in optical beams, so you had sources, you have the condenser lens, and then you want to focus and so on, right? So here we use silica, let's say, lenses if the material is transparent, but then how do we handle electrons? So electrons cannot be handled by simple material, right? So here we are using forces, right? So one is Coulomb and Lorentz force, primarily coming from electric field and magnetic field. We know the force extracted onto this particle strongly depends on the field that is applied. So if you apply an electric field, then you create a parallel and opposite force generated in this electrons, while applying a magnetic field will create a perpendicular force with respect to the electron propagation direction. So by using this magnetic and electric, we come up with electric and magnetic lenses, right? So we use field coils, right? Whether it is electrostatic lenses or magnetic lenses, we use coils. In electrostatic lenses we apply electric field, in magnetic lenses we apply magnetic field. So this is how we control the flow of electrons. So if you take a magnetic lens, so on the right side you can see a very simple cartoon of how we focus an electron beam. So this is the gap that you see here, where you start to make these field lines, right? And then this is the traverse path, and then this is the focal length, right? So from the lens to this is the focal length, and LG, right? That is the gap that creates the field of B, right? So B is the field that is generated, right? And if you look at the focal length, so focal length depends on V, right? So this is nothing but electron velocity, right? So this is particle, so they move at certain velocity, and if the velocity is very high, right, and your field is low, your focal length is going to be long, right? If you want shorter focal length, you want to have this voltage lower so that the acceleration is smaller, and you can use lower field in order to reduce your focal length, right? And that also depends on the size of the lens, right? This gap is the one that creates this field, basically determines the lens or the interaction length and so on. And of course your field to particle to mass ratio is also very important. So that is again a factor here, right, which remains constant to a large extent. So this is how we can make magnetic lens, right? It's a simple coil, right, like we have in our motors and everything, but then we are going to pass electron to this gap, right, and we can control this flow through applied magnetic field, right, which is attained by passing a current through this coil. The next thing is electrostatic lens, right? So we saw magnetic. So electrostatic lenses are slightly simpler to implement, primarily done using coils and plates, right? So when you have a cylindrical electron beam coming in, it will go through 3 plates normally, right. So most of the time these are all integrated, where the middle plate is actually energized, it is at a certain potential, right, while the first plate and the third plate are grounded, right. So through this lens system, by applying various voltages here, we should be able to convert a cylindrical beam to a focused electron beam, right. And we use this the same configuration for doing beam deflectors and so on. So these electrostatic lenses could also be used as a beam deflector, right, where you apply certain amount of voltage to deflect the beam outside the optical axis. So this is the optical axis. So if the beam is within the optical axis, you will capture it, and then if you put a deflector here, right, if I put a voltage here, and then I can deflect the beam, right. So if I deflect it, then I will not see that beam, right, or if you do small deflection, I can change the position of this beam. So these deflectors can also be realized using this electrostatic plates, but you can also use magnetic, right. So one of the interesting thing here is, unlike electrostatic lenses, magnetic lenses create very less distortion, because the field is pretty uniform, right. And the other thing is, they don't create unnecessary second order current inside the field itself. So magnetic manipulation of the beams are primarily preferred for very good beam quality compared to electrostatic, all right. And irrespective of this lens and deflected system, there are multiple apertures we use to profile the beam, to change the size of the beam, right, from one lens system to the other lens system. So this is all integrated into the column, right. And the brightness that you achieve depends on the current that you get per solid angle, right. So if there is a beam being focused, so it depends on how much beam is captured within this particular solid angle, so that the current generated from this. So as we already saw earlier in projection lithography, there is something called a pupil lens, right. Similarly, you will have some blankers here to control the beam size and so on. So based on that, you will know what is the actual solid angle that you get, and that current also depends on the cathode temperature, your current density, and your accelerating energy as well. So this is how one could control how much current you get onto the substrate, right. And the next thing is about the resolution of these beams, right. So what actually determines the resolution, right. So in optical we said lambda over Na, right, times K. So here we discussed about Na, we discussed about lambda, and also we discussed about K, how the process determines the resolution, right. So let's look at what determines the resolution here. First of all, it's a pencil beam, right, it's a very sharp beam. What determines the spot size of this beam is the first question we should ask, right. How sharp is my beam? So that depends on various factors, and that is listed here. So it depends on the diameter of the source, first of all, right, and this is the total diameter, right, end diameter. So what is the source diameter, and what is the diameter because of spherical aberration, right. So aberration are undesirable distortion in the beam that you get. So there is spherical aberration that you get, and then you have chromatic aberration, and then you have a diffraction limit. Okay, so these are all the factors that determines your final spot diameter. So we will look one by one. So just quickly looking at this diffraction limit, right. So diffraction limit is basically your blanket, right, your size of your beam. So if you have a large beam diffraction, what you do is you put this blankers here, right. So what is the size of this blankets and how much we can capture, right, of this diffracted beam is what we call the diffraction limit, right. And in order to control these aberration, right, we need to use the lens system as we discussed, either magnetic, electric or hybrid. Let's see how these things could be done. On the right side you see the effect of the source and your voltage that we use to take the electrons out and focus it, right. So to start with, on the left side is the cathode, right, that is giving you the electrons, and then we capture it through this anode, and then we are accelerating it, and then here is our focal plane, right. So what is the width that we have in this crossover plane is a very important factor, right. So that is RC. So that if you just quickly look at it, right, not very careful, you will see that maybe it depends on the size of the source itself, right. If the source is very small, your crossover might be the width in the crossover will be very small, but if the size is very large, you might have large width. But that is not the case. Actually what determines is the voltage drop across, right. So V naught, so this is your V naught over V, right. So the voltage across your anode, right, is what is determining your width in the crossover point, right. So not just the size of your cathode itself, right. To a large extent it is determined by the voltage that we apply. So let's look at the aberrations, different type of aberration. So there is geometric aberration and there is non-geometric aberration. So geometric aberrations include a spherical aberration, right. This is the beam that is getting distorted. Field curvature, so you always want the field to be uniform, but if the field is skewed, then you will have issues with the projection, right. Astigmatism, chroma and distortion. So this is all the term that one should have encountered in this simple optics, right. So all those things apply here as well, right. So that is what we call geometric aberration. And there is non-geometric aberration. So that is chromatic dispersion and diffraction as well. So these two are non-geometric, right. There is no physical structure that is creating this aberration. On the top, the geometric aberrations are all from the physical structures and creating these aberration. So let's look at spherical aberration. Spherical aberration is nothing but focal length difference between near and far axis of the electron, right. So here you have the two beams here, right. So one is focused and the other one is dispersed, right. So if you look at the focal point, right, your focal point need to focus all the electrons within the distribution at a single point, right. But you won't be able to do that because your lens is also not uniform, right. So you will have the lens dispersion there, and that will come into picture, and that is what is creating variation in the focal length as well, right. So that is determined by the focal working distance of the lens and the solid angle at which is diffraction. As you can see here, it's alpha to the power of 3, right. So very quickly your spherical aberration can affect your focal spot size. Okay, so if you don't take care of spherical aberration, you will have very large spot size where you won't be able to focus it well, and then you will see a very degraded beam because the beam is not focused. It is very broad, and also your current will be low as well. Okay, so this is spherical aberration. And the next thing is chromatic aberration, right. So chromatic aberration comes from the variation in the energy from the source itself, right. So when you have a source, you always expect the source to give out a certain energy particle, right? But unfortunately, you won't be able to get all the time the same energy. There could be a small energy difference in the electrons that are coming out, right? So when there is small energy difference, and that energy difference could result in a distribution, and that distribution will create a variation in the focal, right? So there is a focal difference that you can see here. So if you have just E naught, right, so it will focus here. If there is a change in the energy, then you are going to focus it somewhere, right? So this is what we call chromatic aberration. So chromatic comes from variation in the energy of the electrons that you come in, right? Similar to the chromatic dispersion in optical lenses, right? So all the wavelengths cannot be focused at the same location, right? So there will be slight variation in the focal point between different wavelengths. Similarly here as well. So that is characterized by this, right? Again, you can see here the angle, dispersion angle plays a role here as well, but primarily the energy difference, right, between the central energy and the distribution plays a huge role here. And how do we control this, right? The astigmatism, primarily this is material related as well. When I say material related, the lens system that we use, we switch on and off the system, right, sometimes, and there will be some hysteresis in the lens that will add up and create this astigmatism, right, and we need to constantly correct it. There is no fixed solution to this, right, unlike optical lithography, where you fix the lens and then it should do its job unless the alignment goes off, but here you have to constantly correct it, right. So on the right top, what you see is the effect of astigmatism, right. Without astigmatism correction, you have best focus, it might the spot size itself is pretty large, right, unlike the one with correction. But then when you do defocus, right, so you do over focus, you do under focus. When you do that, instead of the beam becoming larger and blurred, you will have some sort of orientation here. This tells you that the lens is not aligned properly, right. So there is a preferential elongation in one direction, right, magnification in one direction, the other direction you don't see it. So this is a classic example of how astigmatism affects your beam quality. But when you do the correction, so when you correct it, if you do focus and out of focus, you will still maintain the spot nature, right. So it will be always circular, right. So when you do focus, the diameter reduces, and when you do out of focus, the diameter increases. That's all will happen. And then how do we control this? As I mentioned, we use magnetic and electrostatic lenses. So in a magnetic lens, you use magnets, right. So you have the field lines going through, and then the electron beam will feel the force, and then accordingly you can focus. On the other hand, you do electrostatic, where you apply voltage, alternate voltage, that will again create this very nice fringe fields, right, that will make the beam focus in the spot. But more often you use combination lens, right, where you have both electric lens and also you have magnetic lens together. So it gives you a lot of freedom, right, to control the beam quality. And next thing is the beam diameter. What is the minimum diameter that you can define? That this depends on all the non-idealities we discussed, right? The source size, chromatic aberration, spherical aberration, and the diffraction of the beam. So all of this put together determines your beam diameter. So these are all various trends one can look at, and if you combine all of it, you will see the minimum spot size that one can achieve, right? And in order to achieve best beam diameter, one need to address all this. If you just say I will control my source size, I should be able to get it, but you are fixed, right? If you look at source size, it's fixed. You're not going to change the source size. But the other things like the diffraction, your chromatic aberration and spherical aberration are within your control. By using the lenses, you should be able to control it. So by controlling the beam divergence, you control your beam diameter. And the next thing is writing, right? How do we write? So now I have a pencil of beam now, right? So I have a sharp beam, and then I want to write a pattern. So there are two ways to do that, right? So one is called raster scanning, the other one is called vector scanning, right? In raster scan, the beam, if this is the area, the beam scans the whole area, right? And then this is the structure I want to write, and then whenever I want to write, the beam actually comes into the spot, and outside, once it goes outside, the beam is deflected out, right? So when you put this beam blankers, right, so beam deflectors, so you will deflect the beam within this part, right? And then what you will do is when you are outside the pattern region, right, you will deflect the beam outside, right? And it will not pass through the deflector at all. So you do something like this, so that you arrest the beam from exposing the photoresist. So you have, sorry, electron beam resist. So this is the resist that you have, and this is your electron beam, right? So this is raster scan, right? So the beam is always there, and it will be blanked wherever you don't want to write, right? But the beam is scanning all the time. But in vector scan, it is a little different, right? It's a much more sophisticated writing, where you deflect the beam only in the region that you want, right? So the beam will not go outside your region at all. So only the place that you want you will write, and what we call region of interest, and the other parts will not be exposed at all, right? So you need to have a better algorithm here compared to raster scan, which is pretty easy to control by one deflector, but here you need to control much better. And there are two ways of scanning as well. There is line scan and area scan. Line scan writes very fine lines, right? Area scan writes pretty large areas, right? It will normally write very large areas with large currents, right? So if you want very fine features, you use line scan, and the center to center. So it is a spot, right? You move the spot. The center to center spot is kept very close, so that you have fine features, and you normally operate at low energy, okay? Because high energy will always have larger exposure, and if you have lower energy, you will have lower exposure, right? So your exposure is much larger if your energy is higher, right? And this is for energy is lower, right? So your spot size is going to be much finer. And in the area scan, you will have large areas to fill, right? Instead of writing a line, if you have large patterns, you can use this large pattern for writing. And then here the center to center distance is also closely packed, but you use high energy, right? So high energy will give you large area fill. The way we do it is by generating patterns, right, from the pattern generator, which we already saw. So CAD tools can be used to generate these patterns, but this nanometer pattern generator is something that you can buy offline, and then add it to your scanning electron microscope, and you can use your scanning electron microscope as a electron beam writer, okay? So what this one does, it will create the writing field that you want. What is the center to center beam distance, and what is the beam current, what is the dose required, whether it is line or area. So all those information will be put into this pattern file, right? Once it is there, then you take it to the system, and then you can write it. And this is the system that one can use. So on the right side, you see the interface system. So you have the gun, you have the column, you have the final lens system, and then you have your wafer sitting here, right, on the stage. All of this is in vacuum, right? and you need high voltage to generate your electrons, the lens supply to control all the lenses, your blanking amplifier. So this is what is blanking your electron beam when it is not required, right. So if you don't blank, when you move your sample on top of the beam, it is going to expose all the resist. So pattern generator, this is very important, which is going to tell the system where to write and where not to write, and that would require a digital to analog converter that is fed to the deflection amplifier. So here you have the amplifier that is going to tell the pattern deflector where and how much to deflect, and register is for location specific writing, and laser interferometric stage is to keep the stage constant. So you can see here it's not just the column, right. It's a supporting system here with the computer that should be high performing in order to control the beams dynamically. So this is what a system looks like for a e-beam lithography. So unlike an optical litho where you don't have dynamic control of lenses, it's all fixed. Here in electron beam system, you want to have highly dynamic control of the system through these electrostatic and magnetic lenses, so that you get good quality imaging.